Hello, everybody. I will start my today's another live coding session. So in my today's coding session, I will solve this question: coin change. So, yep, I will introduce two approaches in this question: top-down DP and bottom-up DP. Okay, that being said, I will read the question statement. So I'm giving an integer array coins, and this represents coins of different denominations, and an integer amount represents the total amount of the money. Okay. Return the fewest number of coins that I need to make up that amount. If that amount of money can be made up by any combination of the coins, I will return -1. I can assume that I have an infinite number of each kind of coin. Okay. So in this question, I'm giving an integer array coins, and this array represents a unique, maybe not unique, but yeah, every possible option of denomination of coins. And also I'm giving an integer amount. And this is a target amount I try to create with every possible denomination. Yep. And I will return the fewest number of coins. Yep. So that I need to make up that amount. Okay. I will try to create that amount with the possible coins. I can choose any number of coins for each denomination. And that being said, I will try every possible way and I will return the number of coins, minimum number of coins to create that amount. If not possible to generate that amount, I will return -1. Okay, good. So I will, think. Obviously, if the empty of coins array is, coins array is empty, I cannot make up that amount, so I will return -1. But actually, from the constraint, I can find that coins has at least one denomination element. Yep. And also I can find that amount is 0 or larger, non-negative. Yep. Okay. And it doesn't say coins is unique. Yep. Denomination in the coins array may not be unique. Maybe they're duplicated denominations. But yeah. Maybe I can use it as for kind of deduplication as the optimization. This is my guess, but probably it doesn't, affects the time complexity if there is a duplicated one or not. Yep. Okay, this being said, I will take a look at some example. So let's say amount is 12 and coins available is say 3, 5, 2. In this case, obviously, I would think using 6 denomination 2 makes up 12, or also this is possible, or if I use 2 5 denomination, 2 $5 coins, remaining is $2 coin only. So obviously this is the minimum one, I'm pretty sure. Yep. Because, yep, greedily saying I should choose the biggest coin every time. And if not possible, I will choose the smaller coin and continue that. If not possible, I will roll back the decision I made. And then, for example, if I choose 553, then if it doesn't work, then I will roll back the decision 3 and choose 2. And it will be 552. So in that way, I can say the brute force I've just come up with is that I will do the kind of DFS. Yep. So first decision making is which of the coin I will choose, 2 or 3 or 5. And for each, say I choose 5, the remaining is 7. So I have more choices, choosing coin 5 or 3 or 2. And I will try that. Yeah. So I'm pretty sure in that way, I will do the DFS and find every possible, combinations of denominations. Yep. So this is the brute force approach, and the time complexity is, let's say I have coin 2 and amount is 12. In that case, if I choose only coin 2, there's 6 coins I have to choose. So I will think of the upper bound, the loose upper bound of the time complexity, but it should be yeah, like this. So let's assume I have to choose amount divided by mini coin, number of coins. Obviously, if I choose a larger coin, the number should be smaller, but I will think of the loose upper bound. So I will assume I have to choose that number of coins. And for each, I have, yep, every possible coin as the option. Yeah, obviously I can optimize it more with, like, say, the case I choose 5255 can be, kind of compacted as 5 coins 3 times and the remaining, maybe 2 coin X times, 3 coin, $3 coin Y times. So that's another optimization I can make to that brute force approach. But yeah, I will just tell you the upper bound time complexity. Okay. Yeah, I will stop talking about the brute force approach. Yeah, I will think of the, you know, optimized approach. So I can use the top-down DP. So what I mean to say is that, say I'd like to create, say, $10. Obviously, I should choose 2 $5 coin, and that's it. And that being said, if I say I'd like to generate the $12 total amount, I will think of 3 cases. Number 1, choose $2, or number 2, choose $3. Number 3, choose $5. And for each, the remaining is $10, $9, $7. And for $10, I've already calculated it. The minimum number of coins to generate $10 is 2 coins. So that can be used. And in that way, I can solve this question recursively, and also I can use the memorization, because once I find the minimum number of coins for $10, that amount can be memorized as a cache. I don't have to iterate the calculation again and again. So in that way, I can use the, top-down DP. So I can say, so in this case, this is DP equation. And for, the base case, if the argument amount is 0, it means that I could create exactly that amount. So I should return 0. But if this amount is negative, I should return infinity, because it means that I couldn't create the exact amount. So that's the base cases. Okay, but I still can, optimize this. Oh wait, if I do this, the time complexity should be, because for this amount, there are up to max amount severities of, I mean, variations of argument for this amount. And for each inside of this function, I will iterate the number of coins. So this is a time complexity. Yep. Mm, good. Okay. But as I can see from here, each coin amount is quite big, 2 to the power of 31. So yep, but I think this is a working solution. So I will implement this. Yeah, but let me think if there is a more optimized approach. Mm, yeah, good. Yeah, let me start implementation. And for space complexity, yeah, let me talk on that later. But basically, the number of recursion stacks should be up to amount. So because every time I choose one coin, the remaining amount, and each coin is one or larger. So the remaining amount is reduced by one or more. Yeah, that max the number of recursion stacks should be max amount. And for memorization, I exactly want the cache for each amount. And the cache value should be just the minimum number of coins, which is integer, so it's a constant. So it should be max amount. Good. Okay, I will start the implementation. Okay, and I will implement the recursive function. Oh, one thing I forgot to say is for this function, if I cannot create the exact amount, I will return max infinity. I have to handle it in line 39 before returning it. Yeah. I come back to the recursive function implementation. Okay, this is it. Good. Let me yep. Think quickly confirm my implementation with very yeah easy example. Like I try to create $3 and I have $1 and $2. In this case, in line 45, I call minimum coins with 3. And in line 39, amount is not 0, and amount is not negative. So I go to line 44, and the rate should be now infinity. Good. And in line 46, I try 1 coin and 2 coins. So if I choose coin 1, I will call min of, minimum coins with amount minus coin, like this. And for this one, same. 3 minus 2. Yep. So what happens next is in case of this, I call minimum coins 2. So there this amount is 2, which is positive. So I go to line 50 and I choose coin 1 and 2. Yep. And what happens next is that, yep, I don't, work through the code anymore, but I just write the logic here. But in this case, I still have, this is still positive, so I choose coin with 1 or 2. And when this is 0, from line 47, this returns 0. And this is negative, this returns infinity. So in line 33, this returns, mini of this and this, so it should, mini of, oh, I forgot to do something like this. Yep. I return 1 plus the recursive function's result, so I should return mini of 1 or infinity plus 1, so return 1. Okay. And here in line 36, this is already calculated. Wait. Oh, no. So because this is 0, oh, sorry. Because this is 0, I return 0. And in line 32, this should be mini of 1 plus 1 or 0 plus 1. I return 1. Yep. And here, minimum coins 1. This is already calculated in line 33, so this is 1. Yep. So that being said, in line 31, I will return mini of 1 plus 1 or 1 plus 1. They are from line 32 and 37 result. So I return 2. Okay. I'm pretty confident in my code. I work through every line. Just in case I have to check in line 58 if many coins is num coins is the infinity, I should return -1 because exact amount is not creatable. Otherwise, I return number of coins I get from the recursive function. Good. So I covered those lines, so I submit my code again. Good. Okay, accepted. Yeah, so this is a top-down DB approach. Now I will think of the bottom-up DB approach. So in the bottom-up DB approach, I will create the DB table. Yep. So I will think every slot for each amount. Yep. And what I can do is I fill in this kind of slot for each slot. So this, so I will start with 0. Yep. This 0 suggests how many slot 0 suggests, index 0 suggests how many, number of coins do I have to use to make up 0. Obviously, this is 0. And for 1, because I have, let me think with this example. Okay. For this $1, because I don't have $1, I will try $2, $3, $5. And for each 1 minus 2 negative 1, so if I choose $2, I can make it up. So this should be service. I cannot create it. So I pair this with infinity. Infinity means that I cannot create. This works pretty well because infinity, if I compare infinity and other number, which is not infinity, always the minimum one is that not infinity one. So this works quite well. And for $2, if I choose $2 coin, the remaining is $0. I will take a look at 0. So I get 0 plus 1. And for $3, if I choose $3, 2 minus 3 negative 1, which is not impossible. And for if I choose $5, it doesn't work because the remaining is negative $3. So I get 1. Yep. So in this way, for each amount, I will think of each coin to be chosen and look back the, subtracted amount minus chosen coin. Yep. And I will compare those, in this case, 3, patterns. And the minimum one of the total number of coins is the, minimum number of coins to make up that amount, current amount. So basically, I would do that kind of build up from the $0, $1, blah, 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 to target amount dollar. Yep. That's the bottom up DB approach. So for time complexity, because there are, max amount slot, total target amount slot in this array. And for each cell, to fill in each cell, I will think of this patterns where I choose each coin. So it should be this. Yep. For space complexity, I need this slots array. So we should be max amount lengths. So the space complexity should be over max amount. Okay. That being said, I will start my implementation with this. Let me call it DP. Okay. Okay. Basically, this is it. So let me try to work through my code, or maybe let me just explain my code first. So in line 76, I initiate the DP array whose string is amount plus 1 because it begins from 0, 1, 2, then until amount. And the first element, DP0, is 0 because I don't need any coin to generate makeup $0. And then line 79, I try to see for each of amount from 1 to amount. I firstly initiate this mini count with mass infinity, but I notice that I don't have to use this variable. I just have to, initiate the current amount with infinity. So, like this. Then in line 86, 82, I think of each coin. And the remaining amount is this. So, maybe I don't need this rem amount variable. I think this is more concise and intention is clear. Because in line 83, I can say if remaining amount is negative, less than 0, I skip. Otherwise, I update the DP amount with like this. So if 1 plus DP amount minus coin in line 87 is smaller than DP amount, then I will update with line 87. Okay. So in line 87, this one is that I chose that specific coin variable in line 82. So this is 1 coin, and the remaining is obviously DP amount minus coin. Okay. And then line 89, because if the I cannot make up the specific amount, that dp amount cell is infinity, because in line 80 I by default, not the default, but I in line 80 I filled in mass infinity first for each iteration, so it should be mass infinity. Yeah, so in that case I return -1, otherwise I return the dp amount. Okay, so I'm pretty confident in my code, so I will quickly work through my code with very easy example like this. This is a dp table. So first I initiate all rows with null. I actually don't have to initiate this with null. I can start with mass infinity actually, but the reason why I put null is for the debuggability. For the debuggability, if null, I can say it hasn't been filled yet. But if this is infinity and if it knows the expected one, then I can say the logic to update the slot is wrong. So this is for debuggability actually. Yeah. Firstly, this is initiated with 0 in line 84. And here, range should be 1 to amount plus 1, 4. So 1, 2, 3. Okay. So when amount is 1, here, firstly I initiate this with infinity. Then in line 91, I have coin 1 and 2. For coin 1, amount minus coin is now 0. I go to line 94 and dp amount is updated with in line 96, 1 plus dp0, which is 1 plus 0, which is 1. Yep. So now this becomes 1. And when I choose coin 2, in line 93, amount minus coin is 1 minus 2 is -1, which is smaller than 0. So I skip. And that's it about the amount 1. Yep. So I covered all the lines in iteration. So I'm pretty sure about the code implementation itself. So from here, I just confirm my logic. So for amount 2, I will check coin 1 and 2. And in the case of coin 1, remaining amount is 2 minus 1 is 1. So I will take a dp1, which is 1. So this is updated with 2. Then in the case I choose coin 2, if I choose coin 2, the remaining amount is 2 minus 2 is 0, and dp0 is 0, so I get 0 plus 1 is 1. So I update this with 1. So now dp2 is 1. Yep. And finally, I will take a dp3. And for dp3, if I choose coin 1, the remaining is 2. So I get dp2 is 1. So I get 2 as the line 99. So dp3 is updated with 2. Then I will think of the case when I choose coin $2. In this case, remaining amount is 3 minus 2 is $1. So I will take out dp1, which is 1. So I get 1 plus 1 is 2. Yep. So in line 99, 1 plus dp amount minus coin is now 2. So dp amount is updated with 2 and it becomes 2. No change from 2. Okay. So finally, I finished the iteration. So in line 102, now dp amount is 2. Yep. Amount is 3. So I will take out the index 3. So dp amount 3, dp3 is now 2. Oh, so this is not infinity. I will return 2. Okay, so I'm pretty confident on my implementation, so I will submit. Good. Okay, great. So I finished my today's coding session with this. So I will click wrap up. So today I solved the question coin change. So in this question, I'm given an array of denominations of the coins, like 1 to 5. And also I'm given the target amount, like $11. Yeah. And I will return the minimum number of coins to make up the total amount with the given denominations. I can choose any number of coins for each denomination. Yep. And that being said, in my solution, I introduced 2 approaches, top-down DP and bottom-up DP. Essentially, they're almost the same, yeah, just the difference of the implementation. So in my top-down DP approach, the recursive function should be the function which takes the target amount and returns the minimum number of coins to generate that exact amount. And this works quite well because for each, exact amount to be made up, I will think of each coin to be chosen. Yeah. And in that case, the remaining amount is target amount minus chosen coin amount. Yeah. So in that way, I can recursively solve this question and also use the memorization. So this works pretty well. And in bottom-up DB approach, almost the same, but I will fill in the DB table. Build it up from the how many number of coins I need to generate $0, $1, $2, $3, per amount dollar. Yeah. So in that way, I can build up the DB array. Yep. So, and every time I fill in the new cell, I have to look back. I will think of the cases for choosing each denomination, and then I try to generate the remaining amount. And I just have to look back the DB array to get that result. So the same way I can use solve this question kind of recursively. Okay, so that's it. I finished with this. Thank you so much. Bye.